All right, ladies and gentlemen, welcome to the first content lecture of MHA 630 Healthcare Analytics. In this lecture set, we're going to be reviewing some of the basics of statistics. That is, we're going to be going through some of the basic calculations that are necessary to build the rest of the statistics that we'll use in this class. As you'll see, again, this class is focused primarily on interpretation, but we can't approach interpretation without understanding how the values are calculated. And we can't approach the calculation of more advanced statistics without understanding how the components of statistics, or these basics that we'll learn in this lecture set, are created. So that's going to be what we focus on here this week, getting everybody up to speed on some basics review. Now, I call this review. I don't expect you necessarily to have seen this before. So I'm going to approach this as if you don't know these concepts. I will move maybe slightly quicker than I would otherwise. This is a graduate class and it's a short-term class. So I am going to move rather quickly and expect that as you have questions, that you send me an email or that you Google around to learn a bit more as you need. All right, so we're going to start with some big picture concepts up front. These are not going to be calculations per se, but all of these are big picture concepts that will come into play as we talk about the calculations, and are big picture concepts that'll come into play as we discuss interpretations later on in the class. So first, let's talk about some types of data and or study designs. It's really just a couple of general classifications that we use in the field of statistics and evaluation more generally, analytics more generally. First is the concept of a sample versus a population. Now, a sample is a group of individuals often that we gather for the purposes of study, while a population is considered to be everyone that could possibly be of interest. So for instance, if I'm looking to assess the cancer rate in females who are pregnant with a geriatric pregnancy, then what I might look at for that population is all geriatric pregnancy females. That's the population of interest. However, as a realistic note, I'm never going to have access to that information. So if my study or my research or my conclusions are limited based on having access to everybody within the population that I'm interested in, then I would never get anything done. The solution is to gather some people who fit that description, and that is called a sample. Now, there's different ways that we can gather this sample, and we'll discuss this in a second. But broadly speaking, the sample is gathered so that I can use the information from a sample, which I can gather ultimately to make conclusions and decisions. Now, these decisions may affect the population, and in fact likely do. These decisions will affect people outside of just the sample, and in fact likely do. So because of this, it's important to realize the distinction between the sample and the population, and to understand that the sample, one of the goals of getting a good sample in research is to get a sample that in some way represents the population. Similarly, one of our goals with calculations when we calculate quantities from a sample is to understand that we are not calculating quantities from a population. And the fact that we aren't calculating quantities from the population, but the decisions made based on our calculations from the sample may affect the population, should give us a slight bit of unease, as there's a bit of risk that maybe we missed something. This is something that is at the core of statistics and what we really want to make sure we account for, and something we'll be discussing not just for the rest of this lecture set, but in future lecture sets as well. Now, the second, we talked about calculating quantities from sample and populations. What those are called when we calculate a quantity from a sample, that calculation or that calculated quantity, let's say we calculate the mean from a sample, that mean is considered to be a statistic. Now, we can do that same calculation for a population. And if we do it for a population, that calculation is considered to be a parameter. So statistics are a calculation that's made based on a sample, and parameters are simply calculations that are made based on a population. So SS, statistics, go with samples. PP, parameters, go with populations. When I was describing earlier how we calculate quantities with samples to try to make decisions that will eventually affect the population and hopefully affect them fairly, we want our decisions based on the sample to be hopefully one that means something or intelligently tells us something about the population. A more technical way to say that is that we use statistics, again, quantities calculated from samples, to estimate or take a guess at or use in place of parameters, quantities calculated from populations. So often in the realm of statistics, we use statistics to make decisions or to estimate parameters is the way that you'll hear this. Now, this happens, and when we do use statistics to make decisions regarding parameters, that term is called inferential statistics. That's a good one to write down that's not on your slide. Inferential, as in we make an inference or an educated guess based on our statistics as to what our parameters will be. This is something that's going to be the focus of our lectures next week and probably for the rest of class, honestly, but is a really, again, core component of what we do in statistics. We don't just calculate statistics to stand alone, because often the sample is not something that's of particular interest. It's just individuals that we could get access to feasibly. What we really care about is making good decisions regarding the population. Going back to my example of women's risk of cancer who are in a geriatric pregnancy, in that particular case, I don't just want to make decisions regarding the women who I'm studying. I want to make decisions that are going to positively affect all of the women in that condition, even the ones who I haven't studied. That is, I want to use information regarding the parameter so that I can make the best decision possible, all of the women. But that's not realistic to get. So I'm going to use my statistic, that value that is realistic to get, and try to make an educated guess as to what the parameter is. Now, in statistics, what we can do through some of the techniques that we'll talk about in the next lecture set is go above and beyond that. We can make educated guesses, not just about what it should be, but how accurate we think our guess is, so that we don't think that we're being very accurate when we guess based on our sample, a small sample of women versus the population of women. I don't feel like I'm being extraordinarily accurate when in fact I'm not being accurate at all, or vice versa. I'm not too tentative with my conclusions when I should be very confident. So we can attach measures of confidence to these as well, which are going to be a really important tool in communicating our results. So I mentioned earlier that how we select the sample is something we talk about in a second. Now is that second. So when we select a sample, there's a couple of different ways that we can select samples. And actually, there's many more ways than this that we can select samples. But broadly speaking, we can consider samples selected randomly or non-randomly. Randomly tends to be a good characteristic of a sample and indicates that the sample was selected randomly from the population. That is, I took everybody in the population, I flipped a coin for everybody or used a random number generator and selected a particular sample from that population. The reason that this is good is it means that when I make decisions regarding the sample, they are of much higher likelihood to be good guesses regarding the population. Now, consider what the opposite of this looks like. Let's say I did a non-random sample. So let's say I did a sample of a smoking campaign. My wife's in public health, and she always does anti-smoking campaigns. So I feel like to balance out the chi in the world, I have to do a pro-smoking campaign. So let's talk about doing a pro-smoking campaign. So if I went and I stood and I asked, is smoking the best thing ever to a bunch of people, And I decided I can't ask everybody in the world, so I'm going to take a sample. So what I do is I go stand outside of my favorite smoke shop, and for everybody who walks out of it with multiple packs of cigarettes, I ask them if smoking's the best thing ever. And it turns out, based on my non-random sample, that everybody said smoking was the best thing ever. Now, in this particular case, it's clear to see that that non-random sample, the data, that 100% everybody loves smoking data, might represent somebody, but it sure doesn't represent the population of people in the United States or in any particular country for that matter. That is, my non-random sample isn't particularly representative of the population. Whereas if I was forced to take everybody in the country and randomly pick the people I talked to, then that would be much more representative. Note again that this doesn't change the mathematical calculation. And this is something I want you to get the hang of early in this class. Again, in a class that's leaning less towards calculation and much more towards interpretation. Statistics versus parameters. I can calculate the mean for both of those. And both of those can be the same calculation for the mean. That doesn't change the calculation. It changes the interpretation. A random quantity calculated from a random sample versus a non-random sample. That doesn't change the calculation. That drastically changes the interpretation. And it can be very difficult to understand how that changes the interpretation unless I know the specifics of how that non-random sample was collected. So for my geriatric pregnancy patients, let's say I just collected them in my hospital. If I then moved to a different hospital, how do those results translate? Well, that's a good question, and it's kind of difficult because the random selection, perhaps I even randomly selected geriatric patients within my former hospital, that random selection from that population, the population of my previous hospital, now I'm with a new population, a population of a new hospital that random selection may not represent. That is, my previous sample might not be a representative sample of the new population. It was not randomly selected from the new population of patients. Now, it could be that the populations drastically overlap, in which case it probably is going to be a pretty good representation. But to the degree to which these populations do not overlap, it's the degree to which my sample might not be giving me as much or as reliable of information as I need to know. And this actually contributes to another thing that I don't think I have on a slide, but is actually a really important component to think through. When we don't know something in statistics, that's very different than knowing not. Let me say that one more time. When we don't know something in statistics, that's very different than knowing not. So when I say in my new population at my new hospital, I don't know how well the data from my former hospital translate, that doesn't mean that I know not. That doesn't mean that I know that this program that I'm trying to do for geriatric pregnancies does not work. It just means that I don't know if it works or not. It means it's an open question. So in statistics, when we tend to not know things, it means that there's an open question there. It doesn't mean that it's a definitive answer against the context or content that we're looking at. And it's a really, really important thing, and why in statistics we have to be pretty humble because all of our conclusions are resulting around some degree of chance. When we use a sample, it may not have perfectly reflected a population. There's a degree of chance that we're wrong, almost always. But within the random versus non-random sample and the concept of our sample not representing our population, and more broadly, when we just are not sure, again, this should not be taken as evidence against something. This should be taken as evidence that the question is still open. And that's a really, really big concept to understand, especially in the context of medicine. All right, observational versus experimental design. Observational designs tend to be designs that are in nature something that we cannot control, versus experimental designs are things that we typically do have some degree of control over. And I'll admit, when I was in a stats program, I didn't really understand what control meant. So here's what control means. The idea of assigning a drug to someone. So let's say I want to look at blood pressure, and I want to look at how this new drug affects systolic blood pressure. Ideally, the drug would make the systolic blood pressure decrease. So we want to decrease blood pressure in individuals. That's the purpose of this drug. For an experimental design where I have control, I could have individuals who I have come into my office and I control which pills they are given. I can say individual 1 gets pill A, perhaps that's the placebo. And individual 2 gets pill B, perhaps that is the drug. And I can control that to that level what participants are getting. In such a design, that is considered an experimental design because I can control which condition. I'm comparing two conditions, treatment, the drug versus control, the placebo. I can control which condition the participant is in. At any time before I make the assignment, I could point to a participant and say, you are going to be in the treatment group, or you are going to be in the control group. You're going to get pill A or pill B. And because I, as the designer of the experiment, have that level of control that I can assign the individuals to the different groups and then compare what happens with regards to their blood pressure between the different groups, that is what makes a design experimental. Now, we also have observational designs. Observational designs do not afford me that level of control. In an observational design, consider if I'm comparing men and women on their systolic blood pressures. I cannot look at a participant and assign them to the group. I can't look at a participant and ethically assign them to be a male or a female. That's not something that I can do. So because of that, in that type of design, we consider that an observational design. That is, I can only observe the relationships between an individual's sex and their systolic blood pressure, but I cannot control that relationship in the same way. And I shouldn't say control that relationship, I apologize, but I cannot control the group they are in to study that relationship. So it's control of that group membership. That is what distinguishes often between an observational and an experimental design. Now, often in research, experimental designs are considered to be stronger designs. This is actually another great case, too, of where observational versus experimental, the calculations are the same on both observational and experimental. It doesn't affect the calculations we do, it just affects the conclusions we make. And in that context, again, experimental design is considered typically to be a stronger design than observational. On the other hand, there aren't always some cases, or there's not always the ability to do an experimental design type study. One of my favorite published papers of all time is from the British Medical Journal, and I use this a lot in my research design and statistics courses that aren't necessarily medically related, just because of how good this article is. The article is a review of randomized controlled trials. These are experimental design studies in parachute effectiveness. The conclusion of the article is that there are no experimental design studies in the effectiveness of a parachute. Consider what it would entail if there were. We would fly a bunch of people up in a plane, randomly assign individuals to parachute or not parachute, and then throw them all out of the plane and see what happened. Not a particularly ethical design. The reason that this is published in such a high-quality journal is the British Medical Journal. And the reason that such an interesting study is published in a medical journal of all places that seems to have, other than the obvious potential medical impacts of participating in such a study, not a direct relationship with medicine per se, is that oftentimes experimental designs aren't ethical to conduct. This is particularly true in medicine, where we believe in the effectiveness of some particular operations, some particular drugs, and some particular policies that we implement, even if they haven't been tested with the gold standard experimental randomized controlled trial design. However, it doesn't mean that because they haven't ever been examined using an experimental design, that we must then examine them in an experimental design. In the same way that just because we've never tested a parachute with an experimental design doesn't mean that we must test parachutes with an experimental design before we believe that they work. This is part of the foundation behind standard of care, in which we have a baseline set of medical practices that we provide to patients. And we stick to those practices as the baseline. We don't try nothing. Now, we may look to improve standard of care, but we never would compare this to nothing, in the same way that we would never compare a parachute to no parachute. And it's not necessarily, even though experimental designs are the best type of designs, broadly speaking, again, they're not always ethical to conduct, certainly not in medical settings. So it's a fun paper. I'll make that available on Canvas so that you can check that out if you're interested. But the distinction between observational and experimental designs, again, going back to something I mentioned earlier, the calculations are the same in these. But when something is calculated for an observational design, it can have much greater impact than in an in an experimental design. It can have much greater meaning and influence than in an observational design. The reason for this is that if I randomly choose who's in my drug group and who's in the control, the idea is that all of these other factors that I can't control, pre-existing medical conditions, sex, particular injury severity scores walking in the building, etc. All of these other, I'll just broadly lump them in pre-existing conditions and demographics. All of the pre-existing conditions and demographics that I see and don't see in an experimental design of sufficient size are balanced out between the groups. Now, I can explicitly balance out variables too, and that's also good practice. But if I never even know, I never even get to see if the person is male or female, or their injury severity, or their any other pre-existing conditions, if I never get to see that information in an experiment because I'm randomly choosing who goes in what group, that is all balanced out between the groups. That is, there's no systematic distinction between one group and the other that could confound my experiment or confuse my results. For instance, if all the males got assigned in the drug group and all the females got assigned in the non-drug group, how would I know if it were the drug that impacted systolic blood pressure versus the fact that everybody in that group were male? On the other hand, if it were a balanced experiment where everybody was randomly chosen, and on average there's going to be about the same number of males and females in each group, about the same amount of injury severity in each group, about the same amount of pre-existing conditions in each group, etc., that is, both groups are the same, except for the fact that one got the drug and the other didn't. Then in that second case, where both groups are the same except for that drug, it is a better study. It leads to conclusions that focus in on what I'm trying to study. That is, I get to focus in specifically on the effectiveness of the drug, rather this context or conversation about pre-existing conditions or the impact of sex on blood pressure. Now, in an observational study, one of the reasons that observational studies are considered more limited in terms of interpretation, again, calculationally they're the same, but more limited in terms of interpretation, is because that is always a threat. When I have more males in the group, when I'm comparing males and females in blood pressure, and let's say I find a difference. Well, is that because of the males versus females? Is that because maybe it comes out that all the males in the study were overweight and all the females in the study were at a healthy weight? Could that have had an impact? Well, absolutely that could have had an impact. But because I'm just observing, I can't control who got the condition, so I don't have any impact on that. I can't distinguish or tease out, is it the thing I'm trying to study, male versus female in the observational case, or is it this other factor that's also there that, I can't do anything about because I don't have that level of control? So in the experimental design, we feel much more confident that the conclusions are related solely to the thing that we're assigning them to. In my particular example, that my conclusions on differences in blood pressure are going to be related to the drug and the drug only. It's not related to any other factors. Whereas in an observational design, I don't really have that level of confidence in that conclusion. All right, we spent a lot of time on that. I apologize, but that is a big topic and absolutely something that's going to later impact the way in which we make our conclusions. So it's something to definitely take into account even at this early stage in the course. So one other thing that we'll discuss, and this will be the last thing that we discuss on this slide here, is independent variables versus dependent variables. So with independent variables, with dependent variable, how to talk. I apologize. So within the experimental design, where we were assigning the drug to individuals and looking at how it assessed their blood pressure, the dependent variable is sometimes called the outcome variable. And it's not written on your notes, but maybe jot that in, the outcome variable. Independent variable is sometimes called the predictor variable. So these are good additional words that you can jot down and use and might help you get a feel for this. In that experimental design, I assign the drug and I see how does the drug affect blood pressure. The dependent variable is the blood pressure in that case. It's the thing that's being affected. It's the thing that I'm trying to change through the assignment of the drug. The independent variable is the drug that I'm assigning. So I assign something and I expect that something to affect blank. So A affects B is the statement. A is the independent variable, and what it affects. B is the dependent variable. And that could be something nice to write down too. IV affects DV. That's kind of the broad statement. Now, in experimental designs, well, in some experimental designs are necessary but not sufficient to establish causality. That is, in an experimental design, we need to do an experimental design to feel really confident about making causal claims. But an experimental design in and of itself is not good enough necessarily to make a causal claim. We may need more than just that. But in this, our independent variable is the thing that's doing the affecting. A drug affects someone. Being male versus female affects something. That's the hypothesis in the research. The dependent variable is what is being affected. So in both of these cases, we think the drug will affect the blood pressure. The blood pressure is being affected. In the observational, we think being male, female may affect blood pressure. The blood pressure is what's being affected. So the independent variable is what's doing the affecting. The dependent variable is what's being affected. Now, again, in an experimental study is necessary, but not sufficient. We need other things too, to establish causal claims like effect. With an observational study where I just see men tend to have higher blood pressure than women, or vice versa, I guess, depending on my sample. In that type of observational study, I can say that there's a relationship between a person's sex and their blood pressure, but does that prove that being a male was the source of that relationship? Well, not necessarily. There's a great example of this on the relationship between ice cream sales and shark attacks in the Northern Hemisphere. So as ice cream sales go up, shark attacks go up. And as ice cream sales go down, shark attacks go down. And this is a very strong relationship. Now, what's interesting about this study is observational, or that relationship is observational in nature. And it points out the flaw in observational relationships. That is, there could be something else at play. In this particular example that I like, the other thing at play is the seasons. As the season turns warmer to a summer, people buy more ice cream and people go swimming in the ocean, and more individuals are attacked by sharks. As the weather turns cooler, less people buy ice cream, less people go swimming in the ocean in the Northern Hemisphere, and less people are attacked by sharks, or less shark attacks are reported. So in this particular case, again, we see that in the observational type study, that doesn't necessarily mean that just because we found a relationship, it is one affects the other. It's not that ice cream affects shark attacks, that oh, I bought ice cream and now I'm going to go swim in the ocean and sharks like ice cream. So they're going to try to eat it out. Like ice cream caused a shark attack or something. And shark attacks probably don't cause ice cream sales. I don't watch a shark attack and think, oh, I've got to go buy some ice cream. Like that causation relationships are not necessarily how that works. In fact, there's an underlying factor that causes both to happen concurrently. So in observational studies, that is also always a risk, and that risk is reduced in experimental designs. But it's easier to think of independent variables and dependent variables in experimental designs because we do get to use that effect language, even if maybe technically we shouldn't. Again, we need a little bit more than just an experimental design to make effect level conclusions or causal level conclusions. But IV affects DV. DV is what is affected. IV is what's doing the affecting. And that's easier to see in experimental. But again, even with our male, female, and blood pressure, we can still see. We think male, female may have a relationship with or may have an impact on blood pressure. Again, impact on is causal language, have a relationship with, not causal language. So we are careful about that. But it's easier to see with the causal language. IVs and DVs both exist in observational and experimental studies. Sometimes there aren't IVs and DVs in observational studies, but often there are. And it's just easier to see in the experimental design. So we can use that language with almost all observational studies, many. All right, so I've been lauding on and on and on about how all of the calculations are the same, and in many cases that's true, almost all cases that's true, but the interpretations change, and strength of interpretation, and hey, what if we did something like this, or what if we did something crazy like that? I guess I just want to say, hey, I mean it. The reason I mean it is y'all need to understand, as we work with software, I'm not really worried that somebody misses a calculation. Like that does happen. But that's not really the concern with broader research. When I worry about research integrity, it's not that somebody forgot a decimal place. And again, that does happen, but that's not the concern. The concern is that you calculated a number and you didn't know what it meant. You took a statistic and you treated it as a parameter. You took your results from your previous hospital and without thinking, you applied it to your new hospital. You took a non-random sample and you treated it as a random sample. And you gave yourself a lot more confidence than you should have in that situation where your sample really wasn't representative of your population, but you made broad decisions regarding the population from a non-representative sample with confidence. That's not a good thing. Consider the opposite, which is also not a good thing. You had a very, very strong design. You used an experimental design, but out of concern that maybe it wasn't fully representative, even though you had a random sample, you chose to perhaps not implement a policy, which could itself be harmful. If your experimental design with a random sample from a population showed impact, positive impact, and you were, out of an abundance of caution, not willing to implement those results on a broader scale, there could have been harm from the lack of implementation, just like there can be harm from misguided implementation. All this to say, none of what I'm talking about right now has to do with a calculation. It doesn't have to do with messing up typing something into a TI-84 calculator. That's not my concern. My concern is that you misinterpret your conclusions, that you don't know how to evaluate, A, the interpretation of the outcome, B, the strength of the outcome and the strength of the study. And it's important to realize, and I talk about this with some other students in some of our advanced analytics classes, but it doesn't matter where things went wrong, whether your data was wrong, whether the study design was wrong, whether the calculation was wrong, whether the sampling was wrong, whether the results presented were wrong, or whether the conclusions that were eventually made based on this were wrong. It doesn't really matter where in that process things get messed up. If it leads you to the wrong decision, you still made the wrong decision. and individuals or companies still got hurt because of it. My goal is to help you understand how can we make the right decision and avoid some of the problems at the tail end. There's been a number of cases where the entire study was conducted correctly and with fidelity. The results were presented accurately, but the conclusions made regarding the study were lacking. And misinterpreting the conclusions, even if everything else is right, is just as bad as if the numbers themselves were calculated incorrectly. Again, even if it's that last stage that we do that misinterpretation, it still leads us to the wrong conclusions. And again, still leads us to the wrong policy, which can have a negative impact, in some cases, a massive negative impact. So my goal, as you'll see through the rest of class, is to help us with this and to teach us some of these things so that when we interpret this, we can interpret with confidence and at least go through the checklist of some of the basics to figure out where we're at in terms of how confident we should be in our conclusions. All right, well, because this is a class, let's go through a couple examples of some of these different situations and practice just thinking through a couple of situations. Now, again, my goal for you is much broader than this, but this is a class. We gotta do a couple of quote unquote problems. So let's kind of work our way through here. So we've got sample versus population. Let's practice identifying these. So for a sample, data from an undergraduate class. Well, data from an undergraduate class probably represents a sample. It's very unlikely that we only care about the effects of something on that one undergraduate class or that one undergraduate classroom. So this almost certainly represents a sample. Census data. Well, census data representing the broad population of a country, that very likely is a population claim because it represents everybody in the country by law. Data from university. Oh, this one's kind of interesting. Now, in comparison with data from the undergraduate class, data from a university could represent the population. For instance, if I'm speaking to, say, the board of a university, they might not care about anybody else. They just care about the university. And they might not care. One tricky thing for sample versus population, sometimes I get everybody that I care about now, let's say everybody from my hospital or university, in this case, everybody from the university, but I want to make decisions about future people. Well, because I'm making calculations based on different people that I'm making decisions about. I'm making decisions about future patients or future students, but I'm making calculations on past students. That is still a sample, even if I get everybody at the hospital or university. So in this case, it kind of depends on how the data is being used. The data from university, is it being used just to represent what has happened in the past? In that case, if I have the data from the entire university, that could represent the population. On the other hand, if that data from the university is being used to represent students at that university in the future, individuals I haven't sampled, then that would be considered a sample from the broader population, which is all students who have gone or will go to that university. Another interesting thing is that it could be a sample if I'm looking to do conclusions about, let's say, all undergraduate students. Data from one university actually isn't even that big of a sample. So it's nowhere close to the population. Not even thinking about the time thing, looking at future time points, it's nowhere close to the population of students in the country at that time, at that time. So that'd be a relatively small sample. But again, I guess this is a great example of how sample versus population depends on who you talk about. We discussed in the previous slide the concept of moving from one hospital to another and potentially having a good representative sample at the previous hospital, but maybe that doesn't apply to the new hospital because the population that I'm serving has changed. The population of patients at that new hospital is different. So again, that's a hospital by hospital population look. But if I look at the global population of patients, both of them represent pretty small samples. And the same goes for this university. Again, I could just be focused on the university, or maybe I'm focused on the broader student population of students within a country, in which case a particular university would represent a sample, and a small sample at that. All right, random versus non-random sample. Let's see what our examples are. Data from my wing of the hospital. Well, that looks like a pretty non-random sample. It looks like I didn't particularly select a population and then randomly select people from it. So I'm going to go with a non-random sample there. Sometimes these types of samples, not all non-random samples, but this particular type of non-random sample where I get people who are close to me, is called a convenience sample. Using a random number generator. Well, that's a good hint at random. So I'm going to go with random. A random sample if I use a random number generator. To select individuals from blank. AG, the phone book. Well, this is interesting. This is really interesting, actually. So if I use a random number generator to select people from like a phone book or a hospital directory, who is my population? Is my population all of the people or just the people on that directory? And if there's a difference, then this could potentially be random regarding the people it's referring to, but not random regarding the whole population. The phone book's actually a great key in here. I did a study in Fort Collins, Colorado, where we were trying to do public health impact, and we're having a very difficult time getting in touch with individuals because they were not in the phone book. In fact, these individuals were homeless individuals. And data collection with them was very difficult. On the other hand, these were some of the individuals who utilized our public health services the most, and it was very important to gather their perspective. So if I used a random number generator on a phone book, I would have a, quote, random sample as it relates to that phone book, but I would not have a random sample as it relates to the population I was trying to serve. In fact, I would not be representing the population I was trying to serve randomly at all. Now, we weren't just trying to serve homeless individuals. It wasn't a solely homeless endeavor. On the other hand, that was a large component of the population we were trying to serve. So doing the random sample from the phone book isn't necessarily bad, but it definitely was not a random sample as it related to our entire population. It was just a random sample of one particular side of the population and completely missed the other side. So yeah, using a random number, this is a good broad point. When we use a random number generator, all it tells us is who to pick from. But depending on what that book is, where we're selecting names from, unless that book perfectly represents the population of interest, that itself could be a problem. And that's something to really be careful of, especially when you're trying to study conditions that may have disproportional impact on individuals who may not be as represented as others. Telephone surveys is another big one. The types of individuals who have telephone, the types of individuals who regularly use email, may or may not be the types of individuals who you're trying to apply your conclusions to, which means that utilizing services within that context, or excuse me, utilizing research within that context may or may not be inclusive of those individuals. So something to be careful of, something to think through, but that's a good call out on me. Using a random number generator isn't always a random sample. It depends on where you're picking the individuals from. Are the individuals that you're using a random number generator to select from, are they the full population or are they just a subpopulation? For instance, the phone book would just be a subpopulation. That wouldn't be the full population. It's missing the individuals who, in this instance, don't have phones. So that's a good point. That's a good point. All right, observational versus experimental, and IV, that's independent variable, versus DV. So let's look through this. Randomly assign individuals to drug A and B, and C, which reduces chance of CHF. So here, actually, our earlier example is very similar to this. I don't know, maybe pause the video. Can you get this one on your own? Coming back, if you pause it. So this would be an experimental study. Why? Because we're randomly assigning. We have that level of control to drug A and B, and see which one best reduces the chance of congestive heart failure. And, you know, if we have an individual with high risk of CHF, then drug A, or, you know, drug A versus drug B, as opposed to using a placebo, actually makes sense. Again, consider our parachute example from earlier. We have a standard of care that we have to uphold. We can't just give somebody a placebo if they have high risk of CHF. We have to compare them to standard of care. So hopefully we can do better. Hopefully we can continue to improve, but we're not just going to say, you'll be fine, and give you saline. So we said experimental, and then IV versus DV. So remember back, actually, maybe this is a good one. Pause, give it a shot, see. Independent variable versus dependent variable. What do you think this one is? So pause it and give it a shot. All right, coming back. Hopefully you paused, gave it a shot. If not, really do try it out. See if you can figure out the IV and DV. This is one we did earlier, I know. But here, I'll start with the dependent variable, or I'll start with the independent variable. The independent variable is the drug. That's the thing that we control. That's the thing that we dish out. That's the thing that makes the groups. There's a term called levels, L-E-V-E-L-S, levels. The levels of the independent variable are A and B. That's the different options. So drug is the variable, and the levels of that variable are A and B. DV, the dependent variable, is the chance of congestive heart failure, or whether or not you had congestive heart failure. So our DV in this case is CHF. All right. Study if men smoke more than women. Well, yeah, that's good practice. Why don't you go on and pause the video, see if you can put together which one's observational, which one's experimental, which one's IV, which one's the DV. All right, coming back to it. Men smoke more than women. IV is going to be men versus women. So the independent variable would be sex. The levels of the independent variable are going to be men is one level and women is the other. And the DV is the rate of smoking. Now, this isn't really well defined here. Like, what does smoke more than mean? This is actually a fun term you can write down. I don't know if we talk about it later in the class either, but it's an important one called operationalization. So jot that one down, operationalization. But circle more than and write a question mark. That's what operationalization means. It says, what does that mean specifically? Operationalization is really, really, really a great concept in research. But what does smoke more than mean? Does it mean that the percentage of men who smoke is higher? Does it mean that on average, if you're a smoker, the number of cigarettes is higher? And understand that those could be very different questions. It could be that the rate of men who smoke is higher, but women smoke more cigarettes on average than men. So those things can, depending on how that smoke more than phrase is operationalized, this could go in very different directions. In any case, regarding what we're immediately talking about here, and you seriously write down operationalization. That's an important term. And what that means here. But a smoke more than the amount of smoking is the dependent variable. All right. Ice cream and shark attacks. There we go. Well, we already talked about that. So let's just dive right in. This is definitely observational, not experimental. Think about what's required for an experiment. I have to find a whole bunch of people, take them all on the ocean and in a yacht, shove half of them full of ice cream and toss them all in the ocean and figure out which ones get eaten by sharks. Doesn't seem like a very ethical study, just like we can't do the British Medical Journal ethical control trial, experimental trial of parachutes. We're not going to do experimental trial of if ice cream causes shark attacks. So this is definitely an observational study. Which one's the IV and which one's the DV? Well, that's a good point. This, interestingly, is a case where, I think we mentioned this earlier, there's not always an IV and DV. There's not one causal side or one side that we're hypothesizing causes the other. So like in the men versus women, we're hypothesizing that the sex is the differentiator and the smoking more than is the outcome. But here, it's not that the levels of ice cream differentiates the shark attacks or the shark attacks differentiates the level of ice cream. It doesn't really slice down that way. There's not really a good IV or DV here. Now, in the analytics, what that means is that we actually don't have an independent variable, a dependent variable. But don't stress out about that. All it means is it doesn't matter which one you pick. So if you said IV was ice cream and DV was shark attacks, or the DV was ice cream and IV was shark attacks, both of those would work out fine analytically, and they would work out to the same number. Again, because it doesn't really matter in these correlation type relationships. So there's an observational study, and IVs versus DV doesn't really work here. So it's I don't know. At least to me, it looks like a bit of a trick question. Don't expect those on your exam. I'm not a big fan of trick questions. So I guess we don't have exams in the class. Don't expect that on your homework. I'm not a big fan. I guess maybe we can have one of those in your homework. Not a lot of those on your homework by any means. All right. So this has been discussing some of the different types of studies and design, some of the different impacts on interpretation. We didn't even really get to calculations. We're going to keep going. And I think in the next video in this lecture set, we'll get to calculations. But some really good discussion here on how these topics differ: sample versus population, statistic versus parameter, random versus non-random sample, observational versus experimental. All of these are such important concepts when it comes to interpretation. So I highly, 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 highly encourage you, look over this, make sure you're taking notes, rewatch this video if you need to. But these are some of the most important things that I can point out with regards to making comprehensive and well-supported conclusions regarding your use of statistics and statistical storytelling. So this is all super important stuff. In the next video, we'll jump in with things like types of variables and hopefully get to some actual calculations so you can jump in on that. And thanks for sticking with me. We'll see you in the next video in this lecture set.